Hey folks, well, last time we looked at let over lambda to get the kind of idea of an OO-ish approach, and we said that the next time through we'd introduce local functions that would allow us to kind of improve the readability of our code. So just like let blocks, you can define functions that are local to a block. And actually, one of the advantages of this is with a regular old lambda function, you can't call it recursively because you don't have a name to call it by. Whereas with our label blocks, where we can start giving names to local functions, we can actually call them recursively. So again, the idea is the syntax is going to look a lot the same, where we've got this label block, and inside it you've got a list, only this time instead of being a list of local variables, it's a list of local functions. And you can nest these things. You can have label blocks inside label blocks, inside let blocks, inside local block, or inside label blocks, inside let block. You can nest this stuff as deeply as you like. So it's going to be fairly common for us to go through and come up with a structure where you've got a let block for your local variables in a function, and inside that you create some local functions. And the idea would be if you've got a function that you don't use anyplace else, it's kind of a helper function for the one that you're in right now, then you don't need to sort of pollute the global namespace. You just say, okay, well, let's just put it inside this function, the one and only place where it's ever going to get used. So here we'll come up with just a really tiny example where we've got a let block with a local variable x, and inside that we're going to have a labels block. And so this, again, it's just an open bracket label, and then we'll have a list of local functions. So I've got two local functions here, one called getValue and one called printValue, and they both sit inside this list of local function definitions. So for getValue, I'm just going to ask the user to enter some value, I'll read it in and assign it to that local variable x. Right? So getValue is just reading and storing it in our little local space here. And then printValue is just going to print whatever x is so far. And all that my function is going to do, and this is just to illustrate the idea of having these local functions, is to call the first one to get a value and call the second one to print it. So all we're going to do is call one function to read the value from the user, set x, and then print whatever x is. So we're calling this local function, and then we're calling this local function. So pretty straightforward, and it should just go through, and whatever we type in, it'll go through, print out, enter something, wait for you to type something in, and then say, x is whatever you just typed in. Now, again, the idea for, or one of the advantages of this, is that we can have recursive functions in here. So here we've got, and the outer function doesn't matter too much. We're interested in the labels block here. Again, we've got the start of a list of local functions and the end of the list of local functions, and I'm just defining the one here called print. And print just takes some integer, and I think we're doing a countdown here. Yeah, as long as the integer is greater than 0, we'll print it, and then as long as it's greater than 0, we'll call print again on one less than that. So print like 10, 9, 8, 7, 6, 5, 4, etc., etc. So again, this is just an example that a recursive function will actually work, and then the body of the thing that's calling this is just going through and saying, okay, well, if you called foo on whatever the integer is, we'll just call print a on it if a is bigger than 0. So again, just this notion of having local functions and being able to call them. So where we want to play with this right now is looking back at, in the previous example where we had this circle builder function that used let-over-lambda. We're just going to introduce one more layer in between where we set up a bunch of local functions that our lambda can make use of. So again, if you recall in that one, we had our circle builder that was going to create, initialize some hidden stacks or hidden heap space someplace. In this case, having the x and y coordinates of a circle and the radius of the circle. And then it's going to go through and allow us to do things like change the circle to new coordinates, change the radius of it, figure out what the area is, or just print the current coordinates and radius. So what we're going to do is set up a bunch of local functions that allow us to do that, right? So we could set up a set coordinates function that took care of, you give me the new coordinates and I'll set them for you, right? I'll update the local variables. You give me a new radius and I'll update the local variable for that. You call me and I'll compute what the area is from R. You call me and I'll print what X, Y, and R are right now. So we've got this list of local function definitions, and then our lambda function, the dispatcher that we were using, can just say, well, if the user command was set radius, I'll just call this function. If the user command was get area, I'll just call this function. So it simplifies our dispatcher, simplifies our lambda function, because it's just making use of these local methods, these local functions. So again, the idea would be same sort of approach as we went through before, where we do some initialization, right? Check that the user, the parameters that the user passed to build circle were actually valid, and update our stored local variables if they were. And then the interesting part was this lambda function where we said, okay, they can provide a command and then maybe an argument to go along with that. But now we've got a much simpler lambda function, because we're saying, okay, well, if their command was print, I'll just call that print function. If their command was radius, I'll just call the set radius function and pass it the argument that they gave, etc., etc., etc. So it just simplifies our lambda functions. And again, the idea of having these local functions just makes our life in implementing the function a little bit easier. All right, so the scoping and nesting rules are lexical like we would normally expect. The local functions aren't visible outside that label block, just like your local variables aren't visible outside the let block. And again, you can nest these things as deeply as you like. It does get a little confusing if you're not using a good layout. So again, I do recommend using an editor that's got good bracket matching and good highlighting if that's available. What I want to do for a few minutes here is maybe take a look at a slightly more involved example. So let's try, what I want to look at here is creating a dispatcher to manipulate a binary search tree. So we call, build tree or something like that, and it goes through and creates an empty binary search tree for us, and returns a dispatcher for us to manipulate the tree. And then we can start issuing commands to say things like, insert this value, print the tree, search for some value. So this is what we want to take a look at. I think I called this tree builder. How about we treat it as a list? No, I didn't. What did I call it? Which one of these is it? Oh, it's the let-over-lambda-over-labels one. Okay. So for this, again, I'm going to write this as a script so that we can just run it when we're ready to play with it a bit. So I'm going to have my tree builder function that initializes an empty tree and returns a dispatch function. So the only local variable this thing's going to use is just the one that keeps track of the tree. So initially, the tree is empty, so I'm going to use an empty list to represent an empty tree or an empty subtree, and then I'm going to use a 3-element list to represent a tree node. So it would have the first element would be the left subtree, the second element would be the actual value for that tree node, and the third element would be the right subtree. And I'm just going to work with integers here. And we're not going to go through all of the different methods you'd want to support with a tree, but we'll do kind of an insert and a print at least. So I'm going to set up some local methods. Right? So I'm going to have a labels block, and again, we start our collection of local function definitions, and I'm going to have an insert function. And it's going to say, okay, you give me a tree node, and I'm going to handle the root as a special case. So the insert is going to assume you're giving me a non-empty tree node. So this is a case where you're actually giving me something that's, at the very least, it's a list of 3 elements, so left subtree, value, right subtree, and if we need to, we can set or call on the left or right subtree. There. So what I'm expecting from insert is the tree node that you're inserting into, and it's not empty, it's not a nil, and you're giving me the value to insert, and I'm assuming that this has already been tested someplace else, so we know it's an integer. So the possibilities are that n since we know this thing's not empty, so we've already got a value here, so n's got to go either down the left or down the right. So first off, we'll see if it belongs down the left. So if n is less than whatever's in this tree node, then it belongs down the left. And if that's the case, then the two possibilities are the left is null, in which case we can just create a new tree node and stick it there, or the left tree node, the left tree subtree isn't empty, and we'll call insert recursively. So if the left subtree is empty, so that first element of t node, if it's null, then all we'll do is change it to the correct new subtree. Right? So if there's nothing in the left subtree and we need to insert there, then we'll insert a new subtree that's got no left subtree, no right subtree, and just the data value. So we're just updating the left subtree if we need to. Otherwise, we'll just call insert recursively and say, okay, go off and, working on that left subtree, insert this value. So if n belongs on the left, we've got this taken care of it. And if it doesn't belong on the left, it belongs on the right. So if the right's empty, we'll go through that same sort of idea. So if, and again, the right is the third element, so the car of the cutter of the cutter. So if the right subtree is empty, then we'll just replace that nil with our new subtree, right? A list of nil, the n value, and nil. And if the right subtree isn't empty and we're inserting in there, then we just do our recursive call on the right subtree with the current value. So we've got an insert function. I'm going to throw in one just for debugging purposes to print whatever the actual raw tree structure is right now, just so I can take a look at the list structure of this thing if I ever need to debug. So I'm going to call this print ADT, and all it's going to do is print the root in all its grand, glorious detail. And then for our print tree, we'll want to do an in-order traversal of the tree. So I want to go through and print everything that's in the right subtree, and then the current element, and then everything that's in the left subtree. So we'll call print tree on the left, we'll print the current element, and we'll call print tree on the right. And what I'm going to do is skip any empty subtrees, so we're just getting the data values out of this. All right, so then in terms of our dispatcher, right, the lambda function that works on this, again, we're just going through and saying, okay, well, if the command is print, then I'm just going to print this message saying the tree content is, whatever. Call that routine to go off and print it starting from the root, and then I'll just make sure I throw in a new line at the end of it. If they want to insert, then this is where I have to handle the special case where if this is the first thing to go into the tree, right, if this is the root, I'm going to handle it specially. So if the root is null, then I'll just set the root to, and I'll actually build that tree node. And otherwise, we'll call insert on the root. And this is just handling the idea that the insert expects a non-empty tree. So, and again, we want to check and make sure that the argument they provided is valid. So if they gave me an insert command and the argument is an integer, then I'll go through and insert it. And if the argument they gave me wasn't an integer, then I'll give them some kind of error message. For the debug, again, if they give me a debug command, I'm just going to print the raw root structure. And if they give me any other command, then I'm just going to say, okay, that's not valid. And so we'll actually test it out. We'll call our tree builder, right? So that's going off and creating the empty tree and giving me back the dispatcher that I'm just sticking in X here. And then I'll say, okay, insert a 4. And so I'm going to go through and insert a bunch of values. And hopefully what this is doing is, starting off with the 4 in the root, sticking the 6 down the left side, or the right side rather, sticking a 2 down the right side, sticking a 1 down the right side of that, and again, building out this this tree. And when we print it, hopefully we should get the 1, 2, 3, 4, 5, 6, 7 type of thing. So we'll do a bunch of inserts, we'll try a print, we'll try a debug, just to see what the tree structure is so we can see if it mimics what we think it should be. Maybe we'll throw in an invalid command as well. What if we try a fun call X on foo or some such thing? Or we try a fun call X on insert, and I don't know, let's give it blah. All right, so we'll try a couple of invalid ones to see if the error checking is working there as well. So if we try this out, it should go through. And what have we got? Okay, so it actually went through. So there's the results of our traversal. Right, there's the tree structure. So we can see we've got 4 in the root. And again, we've got the left subtree is that tree that's got a 2 and the 2 subtrees. The right subtree has got the 6 in its root and the 2 subtrees. So yeah, the structure actually looks valid. And if we threw an invalid command at it, it said so. If we threw an invalid insertion value, it said so. So we can start building up this kind of data structure, if you like, this dispatcher that we can issue commands through. All right, I will leave that example there.